Conference, your source for JVM knowledge.
So, welcome to my presentation, which I've called Zipfiles on the Fly with Micronaut. So, this is in fact a real-life story that I'm going to explain to you, how you can mess up severely in a problem and at least get it fixed before it reaches production. So I'm going to explain the problem, show you the simple solution that I had a co-worker do. Then we're going to talk a little bit on back pressure and reactive programming, and a little bit on zip files in Java and how they work. And then I'm going to show you how the real solution could be made based on this problem. And all of the examples are in Micronaut. It's a pretty nice framework for both messing up and especially making it a good solution. So my name is Jacob. I'm a senior software architect at a small fintech company called Cartley, based in Odense, Denmark. I'm on the organizing team of the GreatCon, so if you want to hear anything about the conference, ask any of the guys on the first row in the t-shirt similar to mine. And I'm a Groovy ecosystem nerd, and that's partly also due to the guys on the first row. They hired me 8 years ago when I entered the Groovy ecosystem, and before that I have never heard on Groovy. So, we're a fintech startup, and being a fintech startup, we work together with banks. Banks are rather corporate, and I don't think I'm hitting on any banks if I say they might not be the most agile companies to work with. So, one of the banks we were working with says, that's fine, the cloud thing, that might be a thing, but it's not a thing for us. We want everything done in a data center hosted on our national soil. So AWS, sorry, you can't use that. That means that we hired in a data center, and one of the issues with this data center is that storage is just insanely expensive. We do travel expense management. That means people upload their received images, and of course the bookkeeper would like to have those received images, which means delivering those in a zip file is at least one of the possible solutions, which we had to support. So we were not really interested in materializing those zip files, putting them on storage until someone would like to pick them up. So the scenario here is that we would actually prefer to never materialize the zip files until the point where people will really need them, so we could just deliver them on the fly. So that's why this talk came around. So our first attempt was rather straight off the bat. So we can use a zip output stream and just take each of the files, put those in there, get them from the file system, and write them up. Then we end up creating a byte array output stream, and all of this, of course, happening in memory. Then we create a service. So in Micronaut, there's this nice concept of a streamed file. So if you are to deliver a file, you can deliver it as a streamed file. Micronaut picks it up and nicely hands it over to the user. And for this, we can just hand over the byte array output stream. And in the controller, it's very clear what happens. We just have the streamed file, deliver it over, and let Micronaut take care of this. This actually works. It's a good solution, at least from a functional point of view. It works. I can ask for the zip file in plain, and I get it. It's a 40 megabyte zip file, and it just works. It's correct. No problems. See, it works. We tested it. Works on my machine. Put it into production. Things are slightly different. So, remember the non-functional requirements at all times. If you have more than one user on your local machine, things might become different. So, what the solution does is it builds up the entire zip file in memory before starting to serve it. So on my local machine, this of course works brilliantly. But what if multiple clients request a zip file simultaneously? We would have multiple zip files built up in memory at the same time. Even worse, what if they're slow to consume it? We would have a lot of simultaneous connections waiting to stream chunks out of a zip file that we now hold in memory until they're done downloading it. So we can in fact easily test this. So a small bash script that just spins up parallel commands and start Micronaut off with half a gigabyte of RAM. That should be doable for running Micronaut. It can be done with way less. Just with 8 parallel processes, and using curl, we can limit the rate that they download. So here we download with 500 kilobytes per second, and the test result is Java heap space. We die. We don't serve any zip files. That's just with 8 users. So we can, of course, scale this up. We just need to buy a truckload of RAM, put in the machine, but I think this will probably just move the expense to somewhere else. So it's not really a good solution. So the solution that we're looking for is, of course, we should produce the zip file in parts and serve those only when the consumer is ready. So this is a concept called back pressure. We heard it yesterday from those who attended Mary's talk on reactive programming, that we don't want to serve anything that the user is not ready to claim. So a diagram of the naive way is that the client asks the application for the zip file, and we then produce everything, loop over all the files, produce it in memory, and then start streaming it out. So in a reactive way where we could support back pressure, we would definitely want something where the user still asks for the zip file, and then we do a loop where we just take part of a file, dump it into a zip file, and stream that part out to the user. So we'll have a very limited memory footprint at all times. So a little on reactive programming and RX Java. So now we heard what the goal is here. So reactive programming is programming with asynchronous data streams. That means you react to an event that occurs in a stream. A small distinction is reactive programming alone does not make your system reactive. So if you want to read about reactive systems, look up the Reactive Manifesto. Just because we have one small component where we do a bit of reactive programming in does not make our system reactive. But it's a good step on the way. So, in reactive programming, we have the user setting up a connection. So they set up a TCP connection. The TCP connection has some buffers that say how much can I serve at all times. So the window size. So that communicates with Netty and Micronaut at all times saying, yeah, I'm ready for a new chunk. Please stream this to me. So Netty and Micronaut is in this request-response loop. So lucky for us, Micronaut takes care of all the nasty things in that loop. So all we need to do is produce the zip file in chunks and tell Micronaut that it can pick it up in chunks. I've chosen to go with RX Java 2 here. So that's a reactive extension for Java that allows us to do this event-driven and asynchronous applications. And in RX Java, a stream is called an observable. So our goal here must be that we would like to generate an observable that Micronaut and the Netty web server can subscribe to. Observables, they can be hot and they can be cold. A hot observable is, for example, the streams that comes out of a mouse that you roll around. You don't determine the amount of events that happens. Whenever it's moved around, it produces an event. You can decide to listen to them if you're the operating system, or you can throw away a couple of these events. It's hot, you don't decide. In a cold observable, you determine when you want to listen and when you want to start producing things. Hot observables, they definitely need a strategy for handling back pressure. So if your mouse builds up a lot of events and the operating system is not ready to take them, the clear thing here would be, well, just drop a few of these events. The user will just move his mouse a little more to the left if he wants the mouse to go to the left. So here, it's safe to drop some of those. You can also buffer the events, but it's clear if your producer is producing more events than you can handle in your buffer, minus the events that you're already consuming, then you run out of space in your buffer, and you need a different strategy anyway. So buffers are limited. Lucky for us, we can decide when to produce. So we can produce a cold observable. In RxJava, there's a clear distinction between back pressure aware and non-back pressure aware sources. They put that in RxJava 2. So if you produce an observable, those sources doesn't support back pressure. Anytime you need something that supports back pressure, you should use a flowable. A flowable is the back pressure aware source. So the interface for flowable is that flowable of an item emits 0 or n items and terminates with a success or an event, error event. And it supports back pressure, which allows us to control how fast a source should emit items. So we can create a flowable generate with an initial state and a generator. And from the Java doc, it returns a cold, synchronous, stateful, and back pressure aware generator of values. Our initial state is where we set up the relevant state for use when we want to produce the items of the reactive streams. So in our case, we want to keep track of which file should be included in the final zip file, which is the current file that we're streaming from, that we're reading from, and how far ahead in the file that we have already produced. That's all we need in our state. The generator is then where we actually read something and output something, producing the next item that we want to have output. So in this case, that's where we read the next part of the current file and include it in the zip. And if the current file runs empty, of course we need to go to the next file, and if the next file is not there, then we need to close the stream and finish up. So, zip files in Java and Groovyland. We already saw the example in the simple implementation on how we can do this. So, with a zip output stream, whenever we want to include a file, we can actually do it in one of two methods, or modes. A deflated or a stored mode. And deflated is when it tries to do compression. Stored in when it says, all right, so I consider my zip file as just a wrapper around the files that I have. I don't want to do any more processing. The big difference here is when the zip stream is actually outputting. So this is a chunk of code I found deep down in the library for doing this. So if it is deflated, it calls the super to do the write. And the super is where it takes care of the compression. Hidden in there, it says, I'm not going to output any bytes until you close the current file. The danger here when we use deflated is, if I have a large file that I want to include in my zip file, I'll end up having that entire file in memory, again, before I start outputting any bytes. Then we just have moved the problems from the big zip file to a part of the zip file, but I am no longer in control of how big that part is. If the users start uploading big images, I'll end up having big images laying around in memory before I can output them. So the same choice here is to go with stored. So with stored, it just immediately outputs the bytes to the underlying output stream that we give the zip output stream when we create it. So for deflated, compression is used, but no output is produced before a full file is included. So for us, that means it would be dangerous from a memory-wise perspective if we use this mode. Stored, no compression is used. So when I think zip file, I thought, oh, that's a zip, that means it's compressed. So would it be dangerous for us in this scenario to go with this? Not really, in my opinion, because we know we're serving images. If there's anything that the image format does very, very well, it's compression. The JPEGs and the PNGs and the PDFs, they're actually very nicely compressed. If we try to compress them even more, we usually use quality or we don't reduce by any number of bytes. There is a bit of a caveat, however, in using the stored mode. When I ask the zip output stream to start with a file in stored mode, it requires me two things. That deflated mode take care of it all for themselves. It requires the cyclic redundancy check code, which is a computed hash function in a simple way, and it also requires us to have the file size, so upfront when it's added. That means if you are to build a system and use this, it would probably be beneficial to store those values once you've seen the file once. So you don't need to take the file into memory or stream it through your memory to produce this before entering it. So they could be stored in a database, but it's one of those things that you need to take care of yourself using stored mode. So, like I mentioned, since the images are already compressed and due to our memory concerns, we'll try to use stored mode. So, can we do this in Micronaut with RxJava 2? Yes, of course. And it turns out it's actually rather simple. The controller gets a little bit more murky because what we now tell it is that we'll serve an octet stream. So part of what we lose in doing it this way, when we hand over a streamed file, Micronaut knows exactly how many bytes it's about to stream, so it can inform the client that you are now about to receive this many files, go ahead and eat. We can't do it here because we're just telling Micronaut we are doing a flowable with byte arrays. So Micronaut, when it has to serve the initial request, has no idea how many bytes will show up. We'll just continue producing until we say, now we're done, and then Micronaut can tell it, we're done. So because of that, the streaming will be a little different. That means in your browser, you'll have a different experience too. You won't be able to have a bar that says, I have now retrieved 4 megabytes out of 40 megabytes, you're 10% done. We can't do that. So you're just streaming down, you don't know how many bytes it'll become. That's a caveat, and that's something that you need to know. Other than that, we just now return the flowable with byte arrays, and we ask the zip service to produce the zip now in chunks. So that will have to return the flowable. So our service, which returns the flowable, will now set up this flowable. So with generate, we just have the new zip producer state. So we remove all of the nastiness to a class and say, that's fine. The generate function, that should create the initial state, and we'll extract that into a zip producer state. The generator will then ask the state to produce the next element. If it has a next element, then we just emit the unnext, and if it doesn't, that means we cannot get any more, we must have retrieved the last one, and then we can say, well, we complete. In Groovy, you need to tell it that this is a by consumer, otherwise it won't work. In Java, you don't have to do that, but then you would have to write a lot of other code, so still think Groovy wins in the readability. So the zip producer state, let's take a look into that. So the constructor of that sets up all the things that we would want to have in the initial state. So we get a list of file names, and we dump them in there. Then the file repository is where you can ask for the next file and ask for these CRC codes and file sizes of a given file. Then we set up the output stream, and the output stream here is a chunk byte output stream. It's a special output stream that I created for this project that takes byte arrays. So we can serve byte arrays out, and we don't have to serve single bytes, reducing the number of events that we need to take care of significantly. And then the zip stream, which we'll use to produce the actual zip file, because I don't want to take care of all of the nastiness of how should a header in a zip file be, what is the code that and the output that should take care of between the different files. And then of course it says, well, go to next file, make sure that we start on the very first file. chunk output file. I've set the buffer at creation time to 4 kilobyte. That's a decent page size in Linux, so seems like an okay choice. The go to next file is split around 2 slides. So the first case is that we're in fact working already on a current file, and that current file is not out is in the array of the files. So retrieve the file name, get the resource. So in this project, I've just dumped in 20 pictures in the resource folder. So that's how I retrieve it here. Of course, we could retrieve it in any other way. So retrieving them from disk or from a database or from S3. Or, well, if it was in S3, I would probably just dump the zip file in S3. So that was one of the entries here. But I asked the file repository of the CRC code and the size. Then I asked the zip stream to start with this entry, and then the next file I'm going to go to is incremented. Otherwise, I'll just close it up, say I'm finished with the input, so the output stream, if it has a few bytes, would make sure to also write that to the stream, removing the trailing empty spaces, and then say we're done. Then we can produce the next chunk. So if we're done, we just return, there's nothing there. Otherwise, we create a buffer. I ask the current file stream to read into my temp buffer. If it reads something, I determine, did it fill the buffer? If it does, it's just output the entire temp buffer. Otherwise, if I'm at the end of the current file, I won't get the full 4 kilobytes. That means I need to again remove the stuff. If I don't read anything, I can go to the next file. So in the end of files, I might have to produce small chunks. I could, of course, put the responsibility of making sure I always return a completely full 4 kilobyte buffer. But I've chosen to put that somewhere else. Stand still, it works. It almost works. So the zip producer state has these few utilities. So when I produce the next, if I'm not done, and due to the fact that I could produce these very small chunks and the underlying output stream waits until it gets a full 4 kilobytes, then I do this while loop. And I won't expect to go through the while loop more than once. But in case I include a lot of small files, less than 4 kilobytes, I could end up in a scenario where I'd have to ask, well, include more and more files before I have the 4 kilobytes to stream out. Then, of course, the has next and the get next just calls the underlying stream. So with this solution, let's try to test it. So now, instead of starting Micronaut with half a gigabyte of RAM, I'll start it out with 100 megabyte. And instead of running 8 parallel processes, I'll now run 30 parallel processes. Again, I'll limit those to a maximum transfer rate of 500 kilobytes per second. And the test result shows that all the processes have completed, don't get any memory files, and all the files download nicely. So I'll have a demo of this, but some of the key learnings are, if you remember nothing else from my talk than this, remember the non-functional requirements. The first solution that we saw, it solves the problem. If you want to go to a demo after your sprint, you can see, look at this, I can download a zip file. Zip file contains all the images that it should. Everything works nicely. If you put it into production, it'll roll over with memory errors as soon as you have a few people using your system. The zip output stream has those two methods, deflated and stored, and they do behave in a little different way. Not initially. If you use them for creating files, you don't really see it, but under the hood, it makes a difference when you stream out. Of course, if storage and time is not a problem, I would consider sending a link once a zip request is done, and then just put the request on a queue. In that case, I'm always sure how much memory I'll use because I determine how many simultaneous zip files I'm producing. But the user experience, of course, becomes a different one. Now you need to inform your user at some point in time when the zip file has been created that here you go, here you can download your zip file. You can even say once it's downloaded, you can put up a time frame that says, well, then we'll delete it 10 hours later or 24 hours later and clean up. But if storage and time are issues, then I would recommend to go reactive and do this with back pressure. I'll put up the code and the slides in this repository, but just to prove that it's not something that I claim to you, I'll try to start up the project and do the demo. Oh. And startup times matters. That's why at startup time, I'm of course reading through all of these images so that we lower the startup time, we get closer to Spring Boot performance. The reason I'm doing this is I don't have a database in this system, so I just reading the images and in a static array store the CRC code and the size of each file. I made a script to generate this parallel command. So instead of having to type this out, it was way easier to ask Groovy to produce this for me. And as you can see, it is now downloading a lot of different chunks, emitting next chunks every time that any of the 30 processes ask for this. The output is a little murky, but the relevant thing is that you're in the top. Do not see any Java heap space memory. The process dies. You won't be able to download this. I think this takes 3, 4, 5 minutes. So we can leave that and go to questions. Remember, there's the options of giving feedback. So please feedback on the presentation and for all the speakers. And I'm open for questions.
So the Netty web server is embedded in the Micronaut application, I guess?
Yes, it is.
And does it still work if I use an Nginx load balancer in front of it?
That's a good question. I haven't tried.
Okay.
And I don't have the scenario in production, so I think it would, but it's a guess. So don't take my response for good.
Any more questions?
So you are able to do this in Spring Boot 2. And when I say in Spring Boot 2, then I should say in Spring Boot 2, because you can't do it in Spring Boot 1. It doesn't support the Flowable. So another good reason why you should update once in a while.
Questions?
So you can see here, it actually turns out that it downloaded everything. I now have multiple different zip files. If I open one of those, it actually works. Has anyone been in Riga in Latvia? Yeah. I can recommend it. They have excellent food, and if you want to see more photos, all of this is food from my Christmas vacation in Latvia. So. All right. Thank you very much for coming.